Okay, it's 5:30, so let's go ahead and get started today. All right, good evening, everybody. How's everybody doing today? Tired? Yeah, it's that time of the semester. I'm tired too. It's fall semester always feels really tiring just because it takes us so long to get to a break because we're in week 13 right now. And we haven't had a real break in the semester yet. So it's a week before Thanksgiving. So this is always kind of the hardest week to get through. Um, so yeah, I can definitely feel you guys. It's tiring. Okay, and so with that, the plan for today is I'm going to finish up the lecture notes on isoparametric elements. Question. So will this lecture be on the midterm? This lecture will not be on the midterm. And so the last thing that was going to be on the midterm was our lecture last Monday, and also the review video, which was posted yesterday. So the review video, there was nothing new. It's just I was able to go a little bit more detail of that of an example similar to what we did at the end of last Monday, because I know last Monday I was kind of rushed at the end. So if you're kind of struggling with problem 4B on the homework, I would check out the midterm review because I go through one of those problems a little bit more carefully, so I see a bit more step by step. But today is not going to be on the midterms. Today is going to be half of it's going to be for all of this is going to be relevant for your project. So and so today we have a little bit to finish up on isoparametric elements, mostly concerning with the Neumann boundary condition term. And so you're going to use that for your project, but that's not going to be on the midterm. And then after that, we'll actually start to shift the focus from this class away from the theory and more about, what are some practical things that you guys need to know about applying finite elements in practice. So that will apply to, if you're writing your own code, but also if you're using like a commercial software like ANSYS. So a lot of practical things that you guys should keep in mind. Okay? And we're going to start with verification and validation, which which is one of the more important topics for this. Okay. And so let me just kind of, before we start, let me just remind you that Wednesday is going to be our midterm. So this will actually be the last lecture before Thanksgiving. So Wednesday, we're not going to have a lecture. So I'm basically just going to open up the midterm at 5:30 on Wednesday. And then the midterm will be due 24 hours later. So it'll be due on 5:30 on, the midterm will be 5:30 on Wednesday, and then it'll be due at 5:30 on Thursday. So it'll be a 24-hour exam. So just like last time, I'm not going to lecture or anything, but I will open up the Zoom session. So if you want to ask me questions about the exam, I'll be guaranteed I'll be there on Wednesday during that time. I'll still answer messages, throughout the entire exam period, but I might either be asleep or eating something or working on something else. So at least during that time from 5:30 to 6:45 on Wednesday, you'll have kind of my undivided attention for questions at the time. Okay. And then the format's gonna be the same. So I'm basically just gonna upload the PDF for the exam, and then you can just fill out your answers and just upload your answers as just a single PDF. Right? It'll be similar to the last exam where most of the problems will be done just by hand calculations, but you might need to use MATLAB to kind of help you either invert a matrix or perform some calculations. So I'm okay with using MATLAB for those things, but I do want to see all of your work and all of your all of all the setup by hand at least. Okay. And same thing as always. It's this exam is supposed to be it's an individual effort, so please don't communicate with the other students on the exam until the exam period is over. Okay. All right. So are there any questions on that or anything we covered last Monday that I can answer before we get started? Okay. So let's go ahead and get started. And so this will be kind of the conclusion of the isoparametric elements lecture notes. So in terms of importance, this set of lecture notes is probably the most important that you're going to use for the project. And so up to this point, we've covered everything that you need to do for step 1 and step 2 of the project. And so today we're going to go over the Neumann boundary conditions, which is basically going to be the last step and also kind of the more difficult steps. Okay. This title was a lot longer than I thought it was going to be. Okay. Okay, so let's kind of remind ourselves. So the when I say the Neumann boundary conditions, what I mean is something like this, right? So a lot of times you'll have like a 2D element. It could be something arbitrary, looks like this, right? And if we're talking like a heat transfer case, a Neumann boundary condition would be like a heat flux that comes out, something like this. Okay. Oh, question. Lewis asked a question: is today's lecture going to come on the midterm? No, it's not going to be on the midterm. So this is more for your project. Mm-hmm. All right. And so if you have a Neumann boundary condition like this, we know just from previous in 1D, this Neumann boundary condition will make its contribution to the element forcing vector. Okay? Okay. But the way that we apply this in 2D is actually going to be really, really different than in 1D, which is, where a lot of the challenge is. Because if you remember in 1D, when we apply that Neumann boundary condition, all we had to do was basically evaluate the Neumann boundary condition at the boundary node, right? But in 2D, this concept of the boundary is different, right? And so instead of having a boundary node, what we have here is a boundary edge. And so that complicates things quite a bit. And so when we have a boundary edge like this, right, we go to compute our element forcing vector, instead of making just a simple evaluation, what we're going to do is we actually need to perform a line integral. Okay. And so I use this kind of circle on the integral just to denote a line integral. Okay. And then the contents of this integral look like this. You have your four shape functions, right? And all of these are functions of x and y. Okay. And then to that, we're going to multiply by our Neumann value. We Q out. Okay. So for the project, your Q out in this case will be a constant. But because we're doing this integral here, you can have Q outs that are also variable as well. But we're not going to see that for this class because it starts to get pretty complicated in those cases. Okay? And then you integrate over ds. Okay? And so now this integral right here is going to be your Neumann boundary condition term. Okay? And so at first it seems straightforward, right? So because now since our boundary condition is a line, it makes sense that we're evaluating this line integral. Okay? But evaluating this guy and actually computing this, that's going to be where the challenge is going to be. Okay. Okay. Because we're going to need to do something a little bit special with the with the shape functions, because these shape functions, they're defined over the entire domain of our element. But when we actually apply this on just a single edge, then we need to plug in some special values for x and y. Or in our case, since we're doing isoparametric elements, we need to plug in some special values for epsilon not epsilon, xi and eta. But we'll talk about that in a little bit. But before we get there, are there any questions on this? Okay. Okay. And so how do we evaluate this? So the way that we evaluate this, first of all, we have to identify which edges align with our Neumann boundary, okay? Because we're not going to evaluate this over the entire edge, okay? Or we're not going to evaluate this over the entire thing of the element. We only want to evaluate it on the edge that corresponds with the Neumann boundary, okay? And so if we kind of draw the situation from last time and say that we had a Neumann boundary condition on this right side right here, okay? When we evaluate that line integral, we don't want to evaluate it on these edges right here. We only want to evaluate it on this one on the right, because that's where the Neumann boundary condition is, okay? Okay. And so the other thing that we will note is that since we're performing, a line integral is essentially just a 1D integral. And so, just like we've been doing with isoparametrics, we're going to convert this 1D integral into something, into what we call like the Gauss quadrature domain. Okay? So in other words, we're going to convert the integration variable and the integration bounds such that we can perform it with Gauss quadrature. Okay. And so if we kind of start with the form that we had on the previous page, so we had a line integral of n1, n2, n3, n4, and all of these guys are functions of x and y. Okay. Right. And so what we want to change this to is an integral from -1 to 1 of all of our shape functions here. Okay. But now they're functions of xi and eta. Okay. Our Neumann value is still going to be the same, so this is still going to be q out. Okay. Right. Since we've changed the integration bounds, we need to have our scaling factor. Okay. And so this is going to be our Jacobian. Right. Because remember, whenever we change our integration bounds, we have to have some kind of scaling factor here, just to make sure that our integrals will still be the same, right? But since we're just doing a 1D integral, we don't take the determinant of the Jacobian. We have kind of our 1D version of the Jacobian, which was, if you remember, it was dx d xi. Right? So if you remember that from 1D and we computed it, what we got was this value right here for the length of the edge divided by 2. And then we also have our integration variable, which is still s, okay? And so when we evaluate the Neumann boundary condition, it's a little bit tricky because you have to determine, which edge on your element actually has the Neumann boundary condition, which, if you're just looking at the element by eye, that's actually not too hard to do, because we can look at this element above, we can say the right edge, that's the one that we want. But the difficult thing that you'll see in your code is how to get a MATLAB code to determine which edge is a boundary edge. And that's not the easiest thing to do. And so, I won't spoil anything because it's kind of a big part of the project, but that's going to be one of the more tricky parts of the project for sure. Okay. Okay. But we'll leave that for the project. But for the rest of the day, we'll find out how we need to evaluate this. And so, in particular, one thing that we'll see is that in here, we have a little bit of a problem because all of these n1, n2, n3, n4, all of them are functions of 2 variables, right? So they're function of xi and eta, okay? But we're only performing a 1D integral. So, we have kind of a mismatch where we have too many variables, that we can integrate here. And so what we're going to need to do is we're going to need to set special values for these in order to make them one-dimensional functions. All right, question, let me see. All right, so question, just to clarify, in 2 dimensions, a way to verify the determinant of the Jacobian is to calculate the Jacobian of each dimension and multiply J1 times J2. Is there a case where this is not true? Yeah, it's a good question. Yeah, I know we had kind of a good discussion about that last week. I think that's mostly true for the case when your element is kind of, you know, nice and, you know, square and rectangular like this. So like kind of like all the ones in the homework. I have a feeling that that's true if you have kind of a skewed element like this, but it's been a while since I've kind of walked through that proof. So I'd have to kind of look it up and kind of look through my resources. But I think most of the time that's going to be true, just because the structure of the Jacobian matrix and the fact that we're using linear shape functions. But I would need to double check and get back to you on that. All right. Are there any questions on this page before we move on? Okay. Okay. And so how do we go about taking those shape functions and then reducing it in order of magnitude? Okay. And so in order to do that, I want to basically draw our isoparametric element again. I want to kind of draw your attention to a certain quantity or a certain observation. And so this is node 1, 2, 3, 4. And this has coordinates -1, -1. This is coordinates 1, -1, 1, 1, and then -1, 1. Okay. All right. And so in this figure, what I want you to pay attention to are these edges right here, okay? Because that's where we're going to evaluate the Neumann boundary condition. Okay. And I want you to kind of notice that if we travel along these edges, what you should notice is that either xi or eta is going to have some constant value here. Okay. And so on the bottom right here, we can see that if we travel along this bottom edge between nodes 1 and 2, what we see that, you know, we go from -1, -1 to 1, -1. And what we can see there is that eta is going to be equal to -1 throughout this entire line. Okay. And so we can say that if we're traveling on this line, we can set eta is equal to -1, and that's going to be a constant. Similarly, if we travel between nodes 2 and 3 up here, we can see that we go from location 1, -1 to location 1, 1. And so for this entire line, we have xi is equal to 1. Okay? And so that's going to be our constant value. Okay? And then for the top edge, what we see is that our constant value is going to be eta, and that's going to be equal to +1. And on the left-hand side, you know, the left-hand edge, our constant value is going to be xi is equal to -1. Okay. And so this kind of gives us a hint, because you know when we're evaluating our Neumann integral and we're evaluating over these edges, right? And we know that we have to reduce one of the dimensions. Okay? What we can do is that once we've identified which edge is a Neumann edge, okay, once the Neumann edge is identified, we can set one of the variables equal to either 1 or -1, depending on what edge that we're on. Okay. And then once you do that, you've basically eliminated one of the variables from your shape functions, and you can just simply integrate over the other variable. And so with that, if you set one of these guys equal to 1 or -1, then you're just integrating over a single variable like that. Okay. And so I'll kind of formally write this down into an algorithm on the next page, and then we'll do an example to kind of show you how this is used in action. Okay. So before we do that, are there any questions on this? Okay. And so basically here we're going to have two different cases. So basically the first case is if our Neumann edge corresponds to a one of the horizontal faces. Okay. If it's one of the horizontal sides, that means eta is going to have a constant value. Okay. Okay. And so you're going to set eta equal to either +1 or -1, depending on which which edge that you're on. Okay. And so to evaluate the integral, we're basically going to do like this. Okay. And so what we're going to do is we're going to integrate from -1 to 1 of, and I'm going to write shorthand here, so I'm just going to write ni, but you can kind of stack this n1, n2, n3, n4, just like we did before. Okay. And so since eta is going to have a constant value here, we're just going to plug it straight into the equation. So we're basically going to take our shape functions, and then everywhere that we see eta, we're going to plug in either 1 or -1, okay, depending on which edge that we're on. And so the only variable that we have to integrate is just xi, okay? Okay. Right, and so in that case, our integration variable here is going to be, xi right here, okay? So that's why we have that. And if we evaluate this with Gauss quadrature, our formula looks like this. Okay, and so we have the summation from 1 to ng of n evaluated at xi g. Okay, and so that's where we insert our Gauss points. That would be like plus or minus 1/√3. Okay, we're still keeping our eta value equal to our constant value. And then we multiply that by our Neumann boundary condition times the length of the element divided by 2, or length of the edge, and then we multiply it by our Gauss weight. Okay? And so this is what you would use if your Neumann edge was either the top or the bottom of the element. Okay? Right. So in this case, this formula works if you're integrating for the top edge or the bottom edge. Yeah. So in both of those cases, eta is going to equal to either +1 or -1. And so for the top edge, you set eta is +1, and then bottom edge, you set eta is equal to -1. And then now this is the case for the left and right edge. Okay. And so for the left and right edge, it's going to look very similar, except our integration variable will be eta instead of xi. Okay. Okay. And so we're going to integrate from -1 to 1 of ni times xi. So now this one's going to be constant. So this is either going to be plus or -1 eta. Okay. Q out LE divided by 2 d eta. Okay. And this is going to be equal to the sum over however many Gauss points that you're using. Okay. Q out, LE divided by 2, and then WG. Okay. And so depending if your Neumann edge is either on the top or the bottom or the left and the right, you would use one of these expressions here. Okay. All right. Any questions on this before we jump into an example? Okay. Okay. So let's look at the following example. Okay. And so this is going to be the same example that we did last time, except I'm just going to focus on just the Neumann boundary condition. Okay. And so in this example, we had a element that looks like this. Okay. And so let's say that we have a Neumann boundary condition coming out the top like this, okay? And then this Neumann boundary condition had a value of 5 watts per meter squared, okay? And then the other thing that we're going to need for this is the coordinates for all the nodes. So I'm only going to do the coordinates for 3 and 4 because those are going to be the ones on our edge, okay? And so the coordinates for 3 are going to be 0.8, comma 1, okay? And the coordinates for node 4 are going to be 0.2, comma 0.9, okay? Okay. And so we're going to evaluate the line integral for the Neumann boundary condition using a 2-point Gauss quadrature. Okay. Okay. And so the the first step for this is to identify which of our edges is corresponding to the Neumann boundary condition. Okay. Which I know you can see it, but it's good to write it down. Okay. Okay. And so from the figure, we can see that the edge where the Neumann boundary condition is applied is going to be the top edge. Okay. And then for the top edge, the value that we're going to set constant is going to be eta, and we're going to set it equal to 1. Okay. And so that means we're going to be performing our integrals in terms of xi, and then setting eta is equal to 1. Okay. Okay. And so in that case, that means we're going to be working on the first form for this guy here. Okay. And so let's start working on computing each of these guys. And so in particular, let's start by computing the length of that edge. Okay. And so for this, we're just going to use the straight up distance formula. Right? Oh, question. So the reason we use a 2-point Gauss quadrature rule rather than 1 or 3 or 4 points is because the Neumann boundary condition is only between points 3 and 4. That's correct. Yeah. So we're because we're only doing an edge integral here, we're going to use our Gauss quadrature rules for the 1D case. So so actually, for as long as you're using the 1D rules, you can use however many Gauss points that you want. Generally, the more Gauss points that you have, the more work that you're going to do. So most of the time for finite elements, a 2-point rule for 1D and a 4-point rule for 2D, that gives you, the best kind of bang for your buck. So that gives you the most accuracy for the least amount of work. But you can increase the accuracy, or you can take it down one if you want to do less work as well. But yeah, I chose the 2-point rule just because it's usually the best value in terms of work versus accuracy. Okay. And so for the length of the edge, we're just going to use just straight up distance formula. Okay. And so we're going to do x4 minus x3 squared plus y4 minus y3 squared. Okay. Square root of the entire thing. And then what we get from this is 0.6083. Okay. And so let's plug this into our integral. And so our integral is going to be There's a minus sign out in front just because there's always a minus sign for the Neumann boundary condition. And so we have integral from -1 to 1 of our shape functions, the function of eta, or function of xi with eta is equal to 1, okay, times q out, where q out in this case is 5, times the length of the element divided by 2, and then we're integrating over xi, okay? And then we can go ahead and plug this in on the next page and evaluate it with, you know, all the numbers. So before I do that, are there any questions on this? Question? Yes. Yeah. Mm-hmm. Yeah. Just let me know when you're done writing. Okay. Great. Okay, and so let's go ahead and start plugging in values for everything and evaluate the terms. Okay, so if we plug in 5 for q out, and then our length is 0.603, and so we're going to have -5 times 0.6083. Okay, and then we divide by 2, and then from here we're going to evaluate our shape functions at the appropriate points. Okay, so first let's do our first Gauss point. And so remember, for our 2-point Gauss rule, right? And so this is the one that you're using on problem 2 of the homework, right? And so for the 2-point Gauss rule, we have GP1 equal to -1 over √3, okay? And then GP2 is equal to +1 over √3, okay? And so first, let's evaluate it at GP1. And so we're going to set xi, all of our xi is equal to -1 over √3. Okay. Okay. And our eta here is still going to be equal to 1. Okay. Okay. And so that's the first Gauss point. And then we're going to do the same thing, but for the second Gauss point, where all our xi's are going to now equal to +1 over √3. Okay. Okay. And then the same way, you know, all of our eta is going to be equal to 1 still. Okay. Okay. And then parentheses on the side. Okay. Right. So I basically evaluated all the shape functions. So for all the shape functions, I set eta is equal to 1 because that's where our edge is. And then for the xi values, I set them equal to the corresponding Gauss point. So I have one term where all the xi's are equal to -1 over √3, another term where all the xi's are equal to just 1 over √3. Okay. And so you plug all these guys in, right? And you multiply by the factor out in front. What you get is a vector, that element forcing vector, that looks like this: 0, 0, -1.521, and -5.521. Okay. Right. So eta here is going to be 1 for everything, because that's corresponds to our top edge. Remember, we're only integrating over the top edge of our element. Yeah. Mm-hmm. All right, so one sanity check that you can do when you're evaluating these Neumann boundary conditions is you can check which of the entries here are non-zero, okay? And so what we got from evaluating this was that the first two entries of our element forcing vector were 0 in this case. And that makes sense because remember, our Neumann boundary condition took place on the edge between nodes 3 and 4, right? And so nodes 1 and 2 were not active at all, or they weren't even involved in the Neumann boundary condition. And so that makes sense. So because our edge was only between 3 and 4, only entries 3 and 4 of our element forcing vector should have any kind of component in there. Okay, and so that's kind of a nice sanity check that you can do. After you compute your element forcing vectors, just see am I getting the non-zero entries in the right locations. Okay. All right. Any final questions on this example here? Okay. Okay, so that's how you do Neumann boundary conditions. So it's, we did the example here for a quadrilateral, but the project is going to have you use triangular elements. So I do want to take a little bit of time just to talk about triangular elements a little bit because this is what you're going to use for your project. Okay. And so, the isoparametric concept that we just talked about, it's not unique to just rectangles, okay? So you can also use it for triangles as well. So, the concept is the same. So for triangles, we start in the physical space here. Okay. Where our triangle nodes are, we'll call them 1, 2, and 3. And each of these nodes have their own x and y coordinates. So we'll say this is x1, y1. This is x2, y2. Okay. And this is x3, y3. Okay. And so a lot of times, performing the integral on this arbitrary triangle is a little bit difficult. And so we want to map this into an isoparametric triangle. Oh, question. So how does the evaluating the Neumann boundary condition change for 1, 2, 3, and 4 Gauss problem? Yeah, so that's a good question. So, if you want to evaluate this integral with a different number of Gauss points, that's going to change the, the number of evaluations you're going to have here and what eta values that you're going to specify. So let's say that we want to do a 1-point Gauss rule. And so for a 1-point Gauss rule, our GP or Gauss point here is just going to be equal to 0. And so for a 1-point Gauss rule, instead of -1/√3 and +1/√3 and evaluating it twice, you're only going to evaluate the functions once, and you're going to evaluate everything at xi is equal to 0. Okay, and you're only going to evaluate it once. And then in addition to that, we have an additional weight of 2 that we're going to put out in front. And so what you don't see here is that there's a weight of 1 in front of each of these terms. But if we're doing a 1-point Gauss rule, then you have to make sure we use a weight of 2. Yeah. All right, so question, we're just grouping the n times on addition for the sigma. Yes. Yeah, so right, so we're only doing the variation on the xi values, and then we're adding those up because that's the integration variables for that. A question, so where do we get the 0 for the 1-point Gauss method? So that's kind of the predetermined, Gauss point. So if you do a 1-point Gauss rule. So if you want to evaluate kind of a 1-point Gauss rule, a 1D integral with 1 point, the Gauss point is just going to be right in the middle. Right? And so this is -1 and 1. And so you evaluate it right in the middle. So I think we talked about that briefly, and we called it the midpoint rule. Where you just evaluate the integrand in just the middle of the domain, and then that's basically your 1-point Gauss rule there. Yeah. Mm-hmm. And so it's the same as like a 1-point Gauss rule for 2D. So for 2D, if you apply the 1-point Gauss rule, you just evaluate it at 0, 0. And so for 1D, the same thing as if you apply it at xi is equal to 0. Mm-hmm. Yeah. Okay. Okay. And so, oh, question. So derivation of the chart is similar in geometric reasoning. Yes. Yeah. So I think it uses the same rules as we kind of talked about. You kind of have that pyramid of terms. Yeah. Mm-hmm. Okay. So for 2D, W is equal to 2 or 4. So for 2D, if you want to use a 1-point Gauss rule in 2D, then the weight is going to be 4 in that case. Yeah. Yeah. So for 1D, if you use a 1-point Gauss rule, the weight is 2. For 2D, if you want to use a 1-point Gauss rule, the weight is 4. Yeah. Okay. And so our isometric triangular element looks something like this. Right? And so we align the triangle such that it's a right triangle here. And so this point right here has has a coordinates of 1, 0. And this coordinate here is a 0, 1. And of course, this guy down here is 0, 0. And we're going to use the same variable name. So we're going to use xi and eta to be our isoparametric coordinates. Okay. Right. And so if we make this mapping, then our shape functions are going to be fairly simple. Okay. And so these are going to be the shape functions on this element on the right. Okay. Right. And so our n1 of xi and eta is simply just going to be xi. Our n2 of xi and eta is going to be eta. And n3 of xi and eta is going to be 1 minus xi minus eta. So the shape functions here look a lot simpler than for the quadrilateral. So that's one nice thing about triangles, is that the shape functions look a lot simpler. Okay. And so with these shape functions, we can form our mapping. Okay. And so this looks very similar to what we did for the rectangle, right? Except there's only 3 of them instead of 4, right? And so our x of xi and eta is going to be x1, n1 plus x2, n2 plus x3, n3. Okay. And then we have the same thing for y as well. Okay. And so with these mappings here and with these shape functions, you have basically everything that you need in order to compute Jacobians and all that stuff. So we can follow the exact same procedure and the exact same algorithm that we use for quadrilaterals, except now we're using different shape functions, and we have one less thing to evaluate. And so, you know, same procedure, it's just the shape functions look a little bit different. Okay. Okay. And so the biggest difference here is going to be how we actually perform Gauss integration on this guy. Because our shape is so different now, our Gauss points are going to be different, which I will outline on the next page. Okay. So before we do that, are there any questions on this? Okay. All right. And so just like before, you know, the way that we perform these integrals is going to be exactly the same. Okay. And so let's say that we have an integral for x and y. Okay. And so performing this with Gauss quadrature, this is going to be the summation of g is equal to 1 to ng of okay, f of xi g and eta g, okay, the determinant of the Jacobian, okay, times our weight, okay. And so that's going to be our expression, okay. Okay. And so the only thing is, you know, these Gauss points here are going to be different. Okay. And so we're not going to adhere to the same rules because our shape is going to be different. And so let me write you guys a table to kind of summarize what these are. All right, so for triangles, we have a 1-point rule, we have a 3-point rule, and we have a 4-point rule. Okay? So let me organize it like this. Okay. And so if we have a 1-point rule, okay, a 1-point rule is just going to have 1 point. Okay. And so our location for that is going to be 1/3 and 1/3. Okay. And then the weight for this is just going to be simply 1. Okay. Great. All right, so question. So basically, Gauss quadrature is the reason why non-linearly curved elements are used in FEM. Yes, that's it's one of the reasons. But it's you know it's just generally just it's a lot more complicated. But yeah, Gauss quadrature is kind of one reason for that as well, just because it's harder to evaluate the integrals. Mm-hmm. Okay. Then we have a 3-point rule. Okay. And so there's no 2-point rule for this. Okay. And so we go straight from 1 point to 3 point. And so our 3-point rule has the following coordinates. Or 1, 6, sorry. Okay. So that's the first point. And so our second point is going to be 1/6. And then 2/3. And then our third point is going to be 1/6 and 1/6. Okay. And all our weights are going to be just 1/3. Okay. Okay. And then finally, we have a 4-point rule, which is not used that often. So most of the time, either the 1-point rule or the 3-point rule are used. But if you want to step up your accuracy a little bit, you can go up to 4 points. Okay. And then our last point is going to be 0.2 and 0.2. Okay. And our weights here are a little bit strange, so they're not all the same. So the weight for the first point is actually going to be negative, so this can be minus 0.5625. Okay. And then all the other weights are going to be the same. And so W2 is going to be 0.5208. And so will be W3. And W4, okay? And so these are the Gauss quadrature point rules for a triangular isoparametric element, okay? And so I think in the project, what I asked you guys to use is actually this one right here, which is a 3-point rule. Okay? And so just like the 2-point rule for 1D and the 4-point rule for the quadrilaterals, this one kind of gives you the most bang for your buck in terms of the most accuracy with the least amount of work. You know, but different rules exist if you want to, you need more accuracy, if you want to do less computations, you know, depending on what you want from your quadrature. Okay. Okay. Any final questions on this? Okay. All right. So that's the conclusion of the isoparametric element. lecture notes. So I'm glad we kind of took an extra lecture to do that, because I wanted to make sure I go over the Neumann boundary condition a little bit more carefully, because that part's going to be a little bit tricky in your project. Okay. And so from here on out, we're going to kind of shift the focus of this class, because we only have just a couple a few more weeks left. And so I want to make sure I leave you guys with some kind of practical matters for how to apply, or some practical considerations for applying finite elements in practice. Okay. And so the first one that I want to talk about is verification and validation. Okay. And so this is a topic that's not often talked about that much with finite elements, but it's really important, because this is kind of, if you understand this, this is kind of the difference of whether someone will believe your simulations in practice, or if someone will just throw it in the garbage. Okay. And so what we've kind of already seen is that finite element simulations are really powerful tools for engineering design and analysis, okay? Because they basically let us solve any kind of partial differential equation or any boundary value problem that we kind of think of. Okay? And with that, these simulations allow us to avoid, costly experiments, and they allow us to avoid doing really lengthy hand calculations, when the computer does the work, right? But, it's always important to remember that these finite element simulations are nothing more than just a model for reality. Okay. And so it's not like, every time you run a finite element simulation that, that's exactly what's going to happen in reality. Okay. So it's not like, the original works of art. So you can almost think of, finite element simulations as like the Netflix adaptation of reality. So sometimes they're really good, but sometimes they can also be really bad too. Okay. And so, because of this, because finite element simulations can be really bad or really wrong sometimes, there needs to be some kind of ways to kind of test how reliable and how accurate your simulations are. And so that's going to be the subject for this set of lecture notes, for, what are some of the methods that people use to do this, okay? Because when we talk about models here, models are, it's a model is a very, very broad definition. So a model is nothing more than just a prediction for what reality is. Okay. Because, as you'll see, is that there's a lot of really good models and a lot of really bad models. Okay. And so let's do just a very quick example. And so this kind of goes back to, one of our ANSYS projects before, right? So let's say that we have a cantilever beam. Okay. And so we have a beam that comes out just like this. And then let's apply a vertical force like that. Okay. And so what we're interested in is we wanted to find out what's the maximum stress that's going to be in this bar, in this beam. Okay. Okay. Basically, we want to find out if this beam is going to break. Okay. And so, you know, we don't actually want to do this in reality because we don't want to buy a beam on McMaster car and then break it just for the sake of finding out this thing, right? And so most of the time, you know, we're going to use a model to predict this. Okay. And so one way that we can do this is that, you know, we can set this up in ANSYS. You know, we can, you know, apply all the boundary conditions, and we can run the simulation and we can find out what it is, okay? And so that's one form of a model, okay? Another way that we can solve this problem is, you know, is what you guys are going to be more equipped to do, is we can write like a MATLAB code in order to solve this, okay? Okay. And so this is another model. Okay. Or what you can do, which is also technically a model, is you can ask your 9-year-old cousin what he thinks. Okay. And believe it or not, you know, because it fits the definition of simply just being a prediction, you know, this is also a model. Okay. And so all these guys here, they fit the definition of a model, right? But obviously some of these are better than others, right? You know, obviously your cousin is going to give the best answer. So, you know, we want to basically develop some methods or ways to basically show that which of these models are going to provide a better prediction than others. Oh, no, that's cool. Yeah, I didn't know that about ANSYS. So, so Chris is saying that there's a tool in ANSYS called Design Assessment, and it's a way to compare two different models to see, you know, if one is a simplified geometry of the other one. So yeah, that's a good tool. I'll have to look into that. Okay. So are there any questions on this, on what the definition of a model is? Okay. Right. And so when we're kind of presented with so many different models like this, and you know, this list right here is not, you know, the only one. So there's lots of different things that you can do to form a model, right? So you can actually solve the equations by hand. That would be another model and stuff like that. So how do we actually prove or go about showing that one model is more accurate or reliable than the others? And so the answer to that is going to be the title of the set of lectures, which is verification and validation. Okay. And so these two guys, they sound very similar, but they actually have some very distinct definitions. So let me kind of define each of the terms first, you know, before we start talking about them. So let's talk about verification first. And so verification has to do with assessing the numerical accuracy of a simulation relative to the underlying mathematical equations. And so what this means is that, you know, whenever we're solving a finite element simulation, you know, there's going to be an equation on the back end, right? And so we've seen that kind of in our code. So we're solving, you know, a second order differential equation, either in 1D or 2D, right? And so that's going to be, you know, and the thing with verification is we want to make sure that we're actually solving this equation correctly, okay? And so the better way that I think of verification, and the way that I kind of remembered in my head, is verification seeks to answer the question of, are we solving the equations correctly? Okay. And so you know, the debugging and a lot of the issues that you guys are running into in the code right now, in writing, like, like our previous MATLAB exercise and the one you're currently working on for this homework, all of these are issues of verification, right? And so in verification, you have your underlying equation, but it's just an issue of writing the code in order to solve it correctly. Okay. Um, so any kind of typos in the code or any kind of errors or bugs, those are usually issues of verification. Another issue of verification that we'll go over probably at the end of today is actually the quality of the mesh. Okay. Okay. And so, we'll learn something later on today called a mesh convergence test, which is something that you can use to verify the quality of your mesh. Because what can happen with these finite element simulations, if you have kind of a really crappy mesh or a really coarse mesh, you're going to have a really inaccurate solution, right? And so let's say that, we have something that looks like this, like a domain square. If we have just a mesh that looks like this, where we just have 4 elements, this is going to produce a crappier solution than if we have a much more refined mesh, something looks like this. Right? And so in this case, the finer mesh is going to produce a better solution, just because that reduces the amount of numerical errors that we have. Okay. Okay. And so that's verification. Okay. And so the other kind of arm to this is validation. Okay. And so in validation, what this is it assesses the accuracy of your model relative to reality. Okay? And so basically, what validation says is how close are your simulation results to reality. Okay? So unfortunately, we're not going to deal with any issues of validation in this case, because I'm basically providing you with the equations. But validation could be a really important thing, because you want to make sure that you're setting up your problem, in order to get the right solutions. Okay, and so validation is kind of more a question of problem setup. And so these are things are like, are you solving the right equation, right? So are you solving, the heat equation when you should be solving Navier-Stokes, right? Or are you solving like a linear, a linear deformation problem which should be nonlinear, right? And so, we're not going to get too much into this because, we're focusing more on the coding, but it's important to know that, it's important to know, whether you're solving the right equations for the right problem. Okay. And so one common issue that can come up with validation, that's probably seen most often, is setting up your boundary conditions correctly. Okay. because you want to make sure that when you're setting up your finite element simulations, your boundary conditions accurately reflect, what reality actually is. Okay? And so you want to make sure that all your loads and constraints, all your Dirichlet boundary conditions, all your Neumann boundary conditions, they accurately reflect, the real life situation. Okay? And so actually, most of the errors that appear in kind of practical applications of finite elements are usually due to the boundary conditions and making sure that you set them up correctly, right? Because a lot of times it's not easy. So it's not easy to determine, what the correct boundary conditions are. Because you'll have some situations where it's pretty obvious, where it's like, yeah, this surface right here is going to be a constant temperature, or this surface right here is going to be fixed to the wall. But you might have situations where you might have a heat flux, that's due to multiple things like radiation, convection, all sorts of things. And in fluid mechanics, it gets pretty complicated too. And so setting up the right boundary conditions, really takes a lot of effort. And, this is where a lot of people make the mistakes. Okay. Okay. Any questions on this so far? You have a question? Am I going to target a specific percentage for the convergence analysis on this one? So no. So the project, you should be able to reach convergence pretty quickly. I know for the project I asked you to do a mesh convergence, so I just want you to do the plot. So there's not going to be any kind of percentage for this one. Yeah. So what Chris is talking about is that normally when you do a mesh convergence test, we're actually we're going to talk about mesh convergence next. So I'll kind of save it for that. Yeah. All right. Any questions on this? Okay. Okay. So and so the nice thing about this is that, or kind of the not nice thing is that doing V and V, and so that's what this is often called. It's kind of a cute name for something as kind of boring as this, or mathematical, I guess. Is that V and V is actually, if you want to really do it well, it's a very long and very laborious process, because you got to verify basically every single aspect of your code, and you want to make sure that and you actually have to run experiments to make sure that your code is actually validated for the situations that you're in. Okay? But I think for the most part, I think engineers actually use commercial code. So ANSYS is the one that we're using in this class. And so the nice thing about using a commercial code is that a lot of this work, a lot of the verification and validation has already been done for you. So that's kind of what you're paying for. So you pay a lot of money for ANSYS, but you pay that money with the with the expectation that the results that you get are reliable. Right? And so a lot of the work that's associated with verification and validation, that's already been done. Okay? And so the only thing that you have to worry about are kind of these extra bullets that I have down here. Right? And so when you're setting up your finite element problems, you want to make sure that you have a decent mesh with it, and you want to make sure that you choose your boundary conditions and you choose your equations appropriately. Okay? And so if you can do those, well, and they make a lot of sense, then what you can do is you can trust that every other aspect of the code will work correctly, because that's kind of what you're paying for when you're using ANSYS. Okay? And so the thing is with V and V is that these things that I have boxed right here, not only do you have to do them, but you also have to show them as well. Okay? Because a lot of times when you run your finite element simulations, you're going to be required to report these to either your management or to a client or something like that, right? And you need to be able to show to your management or to your client that what you're doing in finite elements is actually reliable. Okay? And so the things that we're going to talk about for this, first thing that we'll do is a mesh convergence test. You want to basically, in the mesh convergence test, what you're basically showing is that the mesh that you're using for your simulation, is actually reliable, and it actually, reduces the errors as much as possible. Okay? And a lot of times this is actually required for doing, any kind of, finite element work. Okay? And so it's important to kind of be familiar with these processes, because it's, you're going to be doing it in one way or the other if you use finite elements for professional use. Okay? Because if you can imagine the alternative, so if you don't perform this work, and so you say that say that you're in the position of management, right? And so you're in the position of management, and then say your boss's son ran something in ANSYS. They said, you know, these are the results that I got. You know, you should buy this $1 million pump because I ran a simulation. I said that it's good, right? And so what I would hope is that you would be skeptical of these results and say, you know, I want you to show me a little bit more. So not just the simulation results, but I want you to kind of show me, you know, that the simulation results that you got are actually, you know, reliable. Okay. And so that's kind of the struggle that you're always working with the simulations. So, you know, one saying that I like a lot is that, you know, because there's kind of a dichotomy. So a lot of people, you know, when they work in this stuff, they either work in simulations, which is kind of what I do, or they work in kind of physical tests, or they work in experiments. And so, you know, there's kind of, these two groups are kind of always warring against each other. So tails all this time. And so what the saying goes is that if you do simulations, then nobody believes your results except for you. But then if you do experiments, then everyone believes your results except for you. Okay. And so, you know, when you're doing simulations, you have the struggle that no one's going to believe your results until you prove it to them. And so the way that you prove it to them is through this stuff. Okay, and so we only have a few more minutes left, so I'm only just going to start mentioning this, and then we'll cover this, you know, we'll discuss this more after Thanksgiving. But the first thing that you should always do in a finite element simulation is to do a mesh convergence test. Okay? And so this kind of falls under the category of verification. Okay. And the kind of the idea behind mesh convergence tests is you want to make sure that your simulation does not depend on your mesh density. Okay. Okay. And so just to kind of give you an example of this, you know, if we kind of go back to the code you're actually working on right now, right? And so I don't know if any of you guys have tried this, but if you computed the results with, say, 2 elements, okay, you might get something that looks like this. Okay, and so you just get kind of something, you know, a curve that looks like that. But if you say you compute it with like 50 elements, you know, you'll probably get kind of a much smoother curve that looks like that. Okay. And so if you overlay these graphs on top of each other, you can see that they're different, right? And so anytime you're performing a finite element analysis, you know, your simulation is going to depend on the number of elements. And generally, you know, as you increase the number of elements, you know, your simulation is going to get more and more reliable, okay? And so the idea with mesh convergence tests is that you want to reach a point, or you want to use enough elements such that your results aren't going to change all that much. And so all there is to it is that, you know, you basically just have to run your simulations with different mesh densities, and you have to show that some quantity of interest doesn't change, okay? But we're out of time, so I think, you know, we'll kind of cover this a bit more after the Thanksgiving break, okay? Okay, so that's all we got time for today. So thank you everyone for tuning in. And so remember, this is our last lecture before Thanksgiving, because Wednesday we have the midterm. And so since this is the last time we'll all be together, you know, I just want to say, hope everyone has a nice, you know, restful Thanksgiving break. You know, I'm not going to assign anything over Thanksgiving because, you know, I want you guys to kind of take a rest, or you can work on the project too. That works as well. And so I'll be grading your midterms over Thanksgiving. So have a great break, everyone. I will see you on Wednesday if you're coming here for the midterm session. But if not, I will see you in 2 weeks. Okay. And so have a restful break. You know, try to, you know, take it easy a little bit, and have a good rest of your day today. Okay. Yes, happy Thanksgiving to everybody. Yeah, so I'll stick around a bit for questions if you have some.
Professor,
Yes.
I have a question regarding the homework. Problem number 3, part
Yep.
B.
Yep. Mm-hmm.
I keep getting a slightly off answer. I keep getting 7,627.
Okay.
Like a couple of hundred, like off.
Uh-huh.
Is the answer that you got correct, or is there a
Uh,
typo?
I did check that one, so I think it was correct. But if it's just a couple hundred off, I think, I'm pretty sure you got the solution there. So probably it might be kind of a rounding error on my part. So I think I wouldn't worry about it too much. I think someone else got kind of something
Oh,
similar
the
to that.
same
So.
answer. Oh, okay. Okay. Thank you.
Yep. Yep. Mm-hmm. All right, so if anyone has any more questions, I'm still gonna stick around. Okay.
Hello. Hi. I guess it's fine. I'm just going to assume that the rest of the participants
Yep.
are there. So I have an interview on Thursday for a design and analysis role.
Okay.
And
Great. Congrats.
Thank you. And I really struggle with like hand calculations when it comes to like, pre-analysis, pre-simulation. Are there any like useful hand calculations that you think I should really know, like right off the bat for like a technical question, or like just any advice in general for like getting through the technical interview?
Yeah, it's a good question. It's been such a long time since I've done that. So what kind of or what kind of company or what kind of work did they do?
So it's at Hyperloop One, and it's like a startup culture.
Okay.
So
Okay.
they want a lot of like rigorous, um, individual analysis.
Got it. Got it. Okay. Yeah, I honestly I haven't applied to a position like that. So I've applied to positions where it's kind of an older company. So the technical questions were more actually conceptual in nature. And so they asked me, can you explain like the concept of like convergence or something in finite elements, or can you explain the concept of like viscous loss and like fluid excuse me in fluid. So that's kind of the technical questions that I've had. I've actually never had to do a calculation in an interview because that sounds very stressful to do. But I think in general, I think what I've always read about those kinds of interviews is that they kind of more are less interested in what the answer to the question that they're asking, but more how you kind of answer it, or like what's your thought process in going to solve it. Because in reality, like the wealth of technical information that they can ask you about is vast, and there's no way to really prepare for it all to really know what exactly that they would ask you to do. But I think it's more just like how you break the problem down, and how you write down information, how you organize your work. I think that's what they would more be interested in. That's kind of what I've read for those kinds of things.
I see. So it's pretty much just safe and sound to assume that if I can pretty much explain the finite element analysis process from concept to simulation and answer, then I should be all right.
Yeah, yeah. So in terms of finite elements, I would definitely kind of go back to our first slides about these are the finite element process of like discretize the domain. First you have to mesh it and make sure your mesh is okay. Then you have to apply boundary conditions, and then you assemble, and then you solve, and then you analyze the results. So yeah, if you can kind of walk them through the process of of either running an ANSYS simulation, or running or even developing the code, like what's your thought process for like how you did like problem 2 on the last homework. I think that would be good preparation for the interview. Yeah.
Got it. Thank you, Professor.
Yep. Mm-hmm.
Have a good night. Happy Thanksgiving.
Thanks. You too.
Bye.
Do you guys have any more questions? Okay. Yeah, no problem. Have a good Thanksgiving, Stephen. Scott, did you have any more questions? Okay. So if there's no more questions, I'm going to close the Zoom call. So if you're coming on Wednesday, I'll see you then. But if not, I'll see you after the break.